Swayam Prabha. Digital India. Educated India.
Welcome back, students. So, in continuation with our module 2, which is mainly focused on enolate alkylation, today we will be talking about lecture 7, and we are mainly discussing on the substrate directed stereo control in different enolate alkylation, and today we will be mainly focusing on enolate alkylation in bicyclic system as well as higher cycloalkanone system. So, this is the few topics which are going to or intended to cover today's lecture, different mode of stereo control in enolate alkylation, substrate directed as we said, and mainly this part is going to be focused in little bit detail, stereo control in conformationally rigid cyclic system. So, that was one of the most significant part in today's discussion. Let us talk about last class we talked about stereo control in cyclohexanone as well as substituted cyclohexanone, how you can control the enolate alkylation stereochemistry with the help of existing stereo center, and we said that particularly ring system like cyclohexanone has its own conformational bias, and based on that conformational bias you can have a predictive model. Now, let us talk about little bit of higher order of cycloalkanones like cyclooctanones. We have a 2-methyl cyclooctanone as a parent substrates, and this methyl group is alpha to the plane, means it occupies the below stereo center, and this is you can eventually if you know the conformational behavior of cyclooctanone, it is basically a mixed kind of conformation. It is contains chair up to this part and this part is boat. So, it is basically chair as well as boat fused form, and this is very well documented in the scientific literature. Now, we will see that once you generate the enolate, you get a planar enolate. The methyl is equatorial in the chair form. It can eventually undergoes conformational flipping to give you another enolate, which also having a similar character. It is basically redrawing the structure. Now, in this case to understand the enolate alkylation stereochemistry, you have to come to here. Now, this part if you see that cyclooctene, which is basically the cyclooctene, which is a chair as well as boat form, and this 3,4 connectivity is basically the enolate pi bond which is formed. Now, the ring is puckered in such a way the bottom face kind of squeezed and the top face seems to be much more exposed on this length. So, top face or beta face, which we call beta face, is much more open, beta face is open or exposed. So, ring structure that gives you, now you can have a definitely a side view, you just redraw it, this particular HOMO of the enolate, you see the HOMO of the enolate, it is drawn in this way, and now the ring, the top face seems to be much more open or flexible, while the bottom face probably squeezed, bottom face is very much squeezed. So, eventually the stereochemistry of this methyl group seems to be not operating at all, it does not take part in anywhere, but the ring dynamics or ring conformational behavior have a well defined predictive role. So, this phase or the beta phase is much more accessible, where the bottom phase only due to the ring structure, the ring is puckered in such a way or twisted in such a way, the beta phase is accessible. So, now this is the drawing, and finally, what we will get, the incoming electrophile will definitely attack from the beta phase, means you get trans. This methyl is already alpha and this methyl has to be beta, but this methyl does not play a role. So, this was the important point. This existing stereocenter probably did not play a role, but the main significant role was played by the ring structure of the cyclooctene. Similarly, a 3 substituted cyclooctanone, you have this stereocenter is beta, means the methyl group is kind of equatorial, is equatorial. Similar way you can actually predict the whole thing again, and here as it is beta, last slide what you have seen, no matter whether it is alpha or beta, the beta phase of the cyclooctene ring seems to be much more accessible. So, here also similar thing happens and the incoming electrophile has to be beta, it has to be beta. Okay. Now, as the present or the pre-existing stereocenter is beta, so you get 1 3 sorry is basically 1 2 3 4 5, yeah. So, these 2 methyl is now become seen to each other, seen to each other. So, the ring geometry or ring conformation of the cyclooctene plays a very important role in predicting the enolate geometry as well as the newly formed stereocenter. Next, we will try to switch over to a very well defined bicyclic system, which is named as decalone. Now, decalones are those systems where 2 cyclohexane rings are fused. Now, first we try to take a decalone, which is normally a alpha decalone or 1 decalone. Now, this 1 decalone you take it as a substrate, you react with LDA, a thermodynamically controlled enolate generation has been taken place. Okay. Now, definitely you have to draw a 3-dimensional structure where you can see that the left hand ring is a flat chair and the right hand ring you can basically try to write a half chair way. If you do not like this drawing, you can eventually switch over to a more precisely half chair in this way. Now, you see that in this case, if you draw in this way, the top face seems to be completely shielded by these 3 hydrogen, this as well as this as well as this. Eventually, if you try to draw this way also, your ring tilting makes this particular portion is not accessible. So, whatever electrophile has to be approached, it definitely will approach from the alpha phase or the below phase. So, if you like this drawing, this line is very straightforward. You can see that the methyl will now approach from the this way, means this hydrogen and this methyl will be now cis to each other, and eventually what will get? You get a cis decalone structure. Cis decalone is this kind of structure. So, that is quite understandable through this kind of drawing, and normally for such a decalone system you can have a very well defined predictive behavior. Things will be a little bit complicated if you are talking about a trans decalone system with a similar kind of. Now, this decalone, as the pre-existing stereocenter we can see, you can eventually try the parent decalone is a trans 2 decalone. Now, this trans 2 decalone means the ring junction stereochemistry is trans. Okay. There is already containing a stereocenter here, but no matter, because we are going to generate the enolate here. So, hydrogen will be abstracted. So, first try to think about the initial drawing. The moment you generate the enolate, this is rigid, it is more of like a 4 tertiary butyl cyclohexanone. So, rigid. So, this cannot flip. So, this ring is a rigid trans decalone. Okay. So, means this is fixed. Now, once you generate the flat enolate, you see this part. So, you only have alpha phase which can be accessible, because now see the top phase was kind of blocked by this hydrogen as well as these are. Okay. So, only approach will be definitely has to be from the bottom phase. So, we have written the everything here. This transdecalon framework is conformationally very rigid, axial attack from the lower phase. Okay. This is definitely has to be axial attack, because there is no other way. Okay. And that will give you directly a chair conformation of the product, and the particular the one alkyl group which is already pre-existing enhances this stereoselectivity. Okay. So, this you can definitely predict. There are higher trans 2 decalon analogues like the examples which you have drawn here. See the first case in the parent compound, in the earlier case we do not have a methyl. Now, I put a angular methyl group here. Now, methyl group is a little bit sterically bulky compared to the hydrogen group. So, now we take this trans decalon with a alpha position having a R group. Now, LDA thermodynamically controlled enolate, a rigid trans enolate has to be generated, fine. Now, where from the incoming electrophile we will now approach. You know, see that the bottom phase is now blocked. Earlier the bottom phase is open, but now the bottom phase is blocked by the angular methyl. Okay. So, enolate flash is flat, it is a flat sp2 system as we are talking about. The bottom phase is definitely blocked. The bottom phase means alpha phase. Alpha phase is blocked. Alpha phase is blocked. So, if alpha phase is blocked, you definitely do not have any other option. The incoming electrophile, the R prime, will coming from the beta phase of the equatorial attack. So, eventually the same thing we have written here. The placement of an axial methyl group at a C10 means this one. In a 2 decalon enolate introduce a 1,3 diaxial interaction. Okay. So, it is with the approaching electrophile. So, the preferred alkylation product now results from an equatorial attack or a opposite side of the enolate. So, this was can be very well explained in terms of a rigid conformational bias of the parent compound. Now, this two examples are a specific example of a enolate generation by Birch condition like lithium ammonia as we said, and both the cases we will be having a ethyl iodide as the electrophile. Now, the interesting point to note that in one of the cases the angular group is a hydrogen and one case angular group is methyl. So, there must be something is playing on here. So, let us go to exactly what is happening here. In the first case when R is methyl, let us talk about one by one. So, first the initial compound which you take alpha beta unsaturated ketone, you treat with lithium liquid ammonia, single electron transfer, you basically get the enolate. Okay. The moment you get the enolate stereochemistry or the conformational bias, you have to draw it. Now, see definitely if you try to draw in a transdecalin feature, that could be much more stable, because now this carbon ion accepts the hydrogen from the nitrogen ammonia as a potent source, and you get the transdecalin as a more stable enolate. Now, fine. Now, the first case R is hydrogen, fine. So, it is not sterically bulky. So, ethyl iodide is the electrophile. The ethyl iodide where from it will come? If it comes from the beta phase, it gets the axial thing. Okay. Now, it is having a parent methyl already in the existing form. Okay. So, now if it approaches from this one, it gets this axial hydrogen in the transdecalin as well as this methyl which is already present. So, there is only one way it can attack from the axial or the top attack. So, if it attacks in the top way, you basically get this as the major product. Now, if R is methyl, the second case, if R is methyl now, in the precedence example or the earlier example we said that if angular position is blocked by the axial methyl, you see the top attack is definitely not favored. Okay. the bottom attack seems to be definitely preferred, though it contains a methyl group, but the angle of approach is not directly contacting. So, you will now get a methyl as a the ethyl as a electrophile, it will be as a equatorial attack. So, the angular group plays a very important role in predicting the stereochemical behavior, and obviously, the transdecaline being the major or stable enolate, you will definitely try to have this enolate as a main structure, and then you can try to predict the existing stereocenter, how it gives a predictive role. Mostly the steric factor is the main determining factor in these two examples, and you can see that typically this angular group R, if it is hydrogen, it gives you one diastereomer, if R is methyl, it gives you another diastereomer. Bicyclic ketone, this particular example is very famous. Now, this particular example what it tells you, this particular bicyclic ketone of this system, where actually the ring fusion stereochemistry is pretty important. Now, what is happening here, the ring fusion stereochemistry, you can see that as the hydrogens are below, means hydrogens are below. So, the around the fusion bond, the ring is basically tilted, the ring is basically tilted. So, these are below. So, ring is kind of tilted. Now, the ring is tilted means the top face seems to be squeezed. So, top face means the beta face is kind of blocked, whereas the alpha face seems to be accessible or open, alpha face is much more open. Now, such a bicyclic ketone, if you now try to generate the enolate, you get these things. Now, this hydrogen as it is pointing towards down, that basically forces, it basically looks like the palm of your hand, where this one cyclopentane is this ring, one cyclopentane is this ring, okay. And then that means that the top face is somehow squeezed and the bottom face is entirely available. And you can see the ethyl iodide, though it is a bulky electrophile, it will basically approach from the bottom face. There is a similar kind of example which is also well documented in the literature. The only difference is you have a amide here, okay, cyclic amide. Now, only difference is we also did it, the ring junction stereochemistry is now cis. So, you have a hydrogen, you have a allyl. Now, this compound is treated with LHMDS and methyl iodide. Now, see that as in continuation with the earlier ring, as the bicyclic ring is tilted downward, means as the hydrogen and the allyl are pointing towards above, the bicyclic ring is tilted towards down. See the drawing which you have drawn it here. And that this kind of drawing basically you can also easily practice in your home. So, what you do? You first draw this fusion bond, okay, and then as relative stereochemistry was given, you might be having a hydrogen, might be having a alkyl group. So, now what you are trying to do? You put these things as this way, and cyclohepentane is as it is an envelope, you can try to put this kind of structure, you can try to put this kind of structure, okay, and you have another hydrogen as the ring junction here. Now, you can easily see this part was more or less very much squeezed or narrow as this. So, one of the enolate face is very much narrow, but on the contrary the top face is more or less openly available. So, always the beta face attack occurs. So, it all depends that how the ring junction stereochemistry is available. Now, there are few assignments were actually designed based on the concept which we talked about. If you try to have a quick look at all the assignment, you can easily do it. Let us talk about the first one. The angular group is methyl, which is the beta one. this stereochemistry is going to be destroyed by for enolate generation. Now, you can see as methyl is above, definitely the alpha attack takes place. The proper drawing you can do it through a half chair conformation, and then you can see this methyl and this methyl is opposite to each other, and you can explain the drawing or the final product. This is basically a keto ester, a ketone and CO2 amine. This compounds already having a 2 existing methyl at this position, angular position. You can eventually draw it. So, no matter you can simply predict that this methylyl bromide will be coming from the opposite of this 2 methyl. Similar thing here, a cyanide is there, this stereochemistry does not matter as it enolate will be generated, angular methyl. So, electrophile will coming from the opposite to the angular methyl. So, very straightforward, very simple, but we will explain it. This particular example is very crucial and very important. You have a bicyclic 1 decalone system with a tertiary butyl at one of the end. I said LDA methyl iodide, you need to predict the product. Now, what happened once you generate the enolate in the TCP mode, thermodynamically controlled enolate, you find this enolate. Now, this enolate you need to draw in the 3 dimensional way. The tertiary butyl group is beta. Okay. Now, if I draw in this way, the tertiary butyl is axial, okay. But eventually tertiary butyl group axial means it gives you a huge 1,3 diaxial interaction in the ring. So, tertiary butyl group try to accumulate in a equatorial position. This can only be possible if the right hand ring flips to a twist boat kind of conformation, but definitely twist boat is not that much energetically preferable, but still that can put you a tert butyl group in the equatorial way. So, this is now a pseudo equatorial position, it is called pseudo equatorial position. Okay. Now, see, now if you try to draw in this way, the enolate kind of being a convex. Convex means now see the bottom face seems to be much more squeezed. Okay. The top face it is much more open, the top face or the beta face is open now. So, if the beta face is open, the methyl iodide can attack from the beta. So, now you see tert butyl and methyl will be cis to each other. So, it is not always necessary that the tert butyl and methyl should be anti to each other, because usually we said that tert butyl is above. So, methyl should be anti, but it all depends the ground state conformation of the starting material. You need to draw the energy minimized structure and then try to draw the enolate and try to now figure it out how the electrophile incoming electrophile approaches from which phase which is easily available. There are few system which we can talk about. There are bit of complex system, complex means polycyclic system. So, beyond the bicyclic we can talk about tricyclic system, and these are mainly based on a specific example which are taken from the literature. The first one seems to be quite easy to be done, is a methyl is already there, is a beta. So, you will be having a exocyclic enolate generation, okay, because enolate will be double bond will be exocyclic or outside of the ring. So, you can definitely try to draw it. Now, as the methyl is above, definitely methyl has to be axial way. Okay. So, you could have a methyl iodide attack from the opposite phase, because this phase seems to be blocked. So, that what does it mean? It means that this methyl and the incoming methyl has to be anti to each other, that is very well understandable. The second one, where a complex parhydrophenanthrene system you treating with potassium tertiary butoxide and methyl iodide. Now, initially you try to draw the ground state conformation by keeping the relative stereochemistry of this all the structures. This is a bit of a difficult if you are not familiar with this drawing. So, this is the hydrogen which will be abstracted which is alpha to the aldehyde, this hydrogen, fine. So, this you can have. Now, see the initial drawing, acyl acetate group is below chair another chair, another chair. Now, see this hydrogen, this hydrogen, this methyl and this hydrogen all are kind of. So, this hydrogen is this hydrogen, hydrogen 1, hydrogen 1, this is the next hydrogen will be hydrogen 2, then you have this, then you have methyl, then you have hydrogen. So, these are all are very perfectly matched. You draw the exocyclic enolate, fine. Now, you can see that the entire, as the ring is tilted, this part seems to be more or less squeezed or closed, but this face is entirely available. So, the enolate will be definitely attacked through axial attack. Now, you can see the methyl is above. So, this methyl is below, that you can explain actually, but anyway until unless you draw the entire structure, drawing of the final product stereochemistry will be bit of difficult for you. On the similar way, you can also explain couple of other things. The first one and the second one is more of like a Birch reduction. If you try to remember, if you have a simple benzoic acid, which you subject to Birch condition means sodium and liquid ammonia. Now, this condition usually you know that the deconjugated system will be happening, but definitely you get a carbanion alpha to the carboxylic acid. Now, this is usually will then undergoing a enolate formation OH, or you can have a ONA. Now, this is what? This is the enolate generation. So, in this way now you can see that the existing compound contains a beta carboxylic acid. So, the methyl iodide approaches from the opposite to the carboxylic acid, very straightforward. Same way this is alpha carboxylic acid. So, methyl opposite. This one is a little bit complicated, where actually gamma alkylation takes place. Initially the hydrogen, there is actually it is a more of like a thermodynamically controlled condition, because base is weak. So, this actually abstracts this hydrogen. So, this is abstracted and you get this is as a enolate. So, this enolate once you get, you actually you will now trying to have this attack on this particular position. Now, see this group is beta, this group is beta, this group is beta. So, methyl is coming to alpha, and this is example or intermediate for the lanosterol synthesis in the cholesterol synthetic pathway. Now, few more examples which we have discussed in the last class. Actually, this is just like a to give you a refreshing memories. Cyclic stereo control in the 5-member ring. If you have a system like this, that you have a basically a beta stereo center here, and you see it is a pretty bulky group, it is a trityl group, you see trityl group, and means that the hydrogen which will be abstracted from here, you generate the enolate, and then as this is beta, this attack will be from alpha phase. Okay. So, this is the preferred conformation of the enolate. You can basically try to twist little bit just for trying. This one is pretty simple. You have a parent compound where both the phenyl and methyl will be beta, means above the plane. So, now you can eventually try to draw it. The incoming electrophile has to be alpha, because its beta phase is exclusively blocked by this 2 bulky group. So, these things are pretty much simple, and you can eventually try to do it. This example was again a example of a acyclic stereo control, but here what is much more important that one of this oxygen in this acetinoid protection can actually take part with his chelate formation once the enolate is generated by abstraction of this hydrogen. Okay. So, it forms this kind of things. Now, the existing stereo center is this is beta. So, beta means the enolate which is there, it is also this way. Now, the way it has been drawn actually, it was bit of difficult to conceive, but this aryl group plays an important role. This aryl is below, so this methyl is coming from the opposite way. Okay. So, this is the main acyclic. So, this structure is kind of a acyclic stereo control, but it acyclic stereo control through a cyclic chelate. So, it can also categorized through a acyclic stereo control through cyclic chelate formation. So, at one side this become acyclic stereo control, in the another side it becomes cyclic stereo control. So, as a concluding remark, we can say that we are basically trying to cover in today's class mainly alkylation of several bicyclic ketones as well as a few polycyclic systems. We talked about the conformational rigidity, which plays a very important role. The more rigid the conformational is, it is having a certain conformational bias, and then you need to know the ground state conformational behavior of those starting materials or the precursors, which plays a very important role. So, thank you. We will see you again in the subsequent week.